Good morning, class. This is 2.3 matrix operations. The objectives here are to describe matrices using matrix terminology, to add and subtract two matrices, and multiply a matrix by a single number called scalar multiplication, and then multiply two matrices together. So here's some matrix notation. A row is a set of numbers that are aligned horizontally. So let me show you what that looks like. Well, let me highlight. So see, these numbers right here are all in the same row. And the the this notation A sub 1, 1 means whatever value is in this top left corner of the matrix. It's in, this is called row 1, and that's and the first number that's a subscript here, let me highlight that in pink. This first number is showing you the row that that each one is in. So this is all row number 1, and we look at the second row, second vertical column here. See, look, we have a second vertical. I'm sorry, it's horizontal. It's going left and right. It's horizontal, so that's the second row. And notice how everything in the second row, that first number subscript is 2, because that's indicating the second row. Okay, you can't see that. You couldn't see the green and pink together. Those didn't match. So let me see. See this, like the number here, the sub 2 means that these are in the second row. And then the second number that you're looking at, that's referring to the column. So I'm just going to erase everything we've done so far. So then, okay, so this is aligned horizontally. Horizontally is like a flat line, like the horizon. Okay. When the sun rises in the day, the horizon, right? So that's the number of rows. A row is a set of numbers that are aligned horizontally. Then a column is a set of numbers that are aligned, you guessed it, vertically. And vertically is up and down, right? Now we're talking about like the height, how far up and how far down, right? Vertically. So look at the vertical column. So this is a column here. And that's why we see that the second number is indicating the column, and it is a 1. There's a 1. The second number here is always a 1, because this is all these numbers are in the first column. Then you have the second column. All the numbers here are in the second vertical arrangement here. And then so you see that the second number is a 2, saying that 2 is indicating that these numbers values are in the second column, and so on. So that is, and I'm skipping the third column, right? But then they're saying in the matrix A here, the entry in row 2, column 3, is A sub 2, 3. So it's the second row, down 1, and then the third column. So 1, 2, 3. So there it is, the term in the second row and the third column, which is denoted A, 2, 3. There we go. A row matrix is a matrix just made up of one row. Like this row, this matrix above is made up of three rows and three columns, right? One, two, three, and one, two, three. But a matrix that's just a single row, that is, and it could be longer, but I just made three in it. That is called a row matrix. And then a column matrix is the same thing, but like made of a single column, right? And so it'll be A1, 1, A2, 1, A3, 1. There you go. And just make sure I have my right notation here for everything. Okay, yeah, it looks good. Okay. Now, a matrix is a regular array of any numbers. I'm sorry, that is, and they like to use a capital letter to talk about a name instead of naming it like a name like Fred or whatever, like they would do with hurricanes. They rename it. A hurricane is named Fred, or they name it. I actually don't know exactly something alphabetically with the names. Well, with matrices, we just refer to a particular matrix with one capital letter, and they'll be called this one matrix A. And it says, what are the dimensions of matrix A? And when they ask for dimensions, they mean what are the number of rows? They like to list the number of rows first, and then the number of columns. So notice matrices are often referred to in dimensions m by n. When it were the it looks like m times n, but they're not saying that. It's just a notation to show that you have m rows and n columns. So the given matrix here, I can see it has 1, 2, 3 rows. So it's going to be 3, and then it has 1, 2 columns, so 3 by 2. And what are the entries for 3, 2? So that's going to be the third row, right? Because the first digit there is a row, and the second column. So third row, 1, 2, 3, and second column. So the entry there is 1. The value that's in that spot in the matrix is 1. And I say, what is the entry? Which means what is entered, like in that spot for 2, 1. Well, this is this second row, right? Because the 2 there means row, and it's the first column. So second row, so there's the first row, second row, and first column. So right here. So A sub 2, 1, what's in that entry, what's in that spot is a 2. And there we go. Finding the sum and difference of two matrices. So given matrices A and B of like dimensions, addition and subtraction will produce a matrix C or D of the same dimensions. So they wrote it like this. Let's see even closer here that, let me explain this notation to you. What they're saying here is when we add matrix A to matrix B, we're going to get a matrix, let's call it C. Now, the A sub ij are, the I stands for a given row, and the J stands for a given column. And they're saying we're going to take, let's say an entry in matrix A, let's say it's in column 1 and I'm sorry, row 1 and column 2. Well, we're going to add that same entry in that same spot, but from matrix B, we're going to add that same value in the same spot from row 1, column 2, and that's what's going to produce for us the entry in the new column of C, and then we're going to place it in C in that same spot that was located in A and B. So we'll see what that looks like. And the same thing, and very similarly for subtraction. So let's see, they do make note here that matrix addition is commutative. So it doesn't matter which way we add these, and it's associative. So if there's multiple sum addition operations that we have to do, it doesn't really matter which way we do first. So they say, give A and B, find the sum. So if I add them, just like I said a minute ago, this is not bad. I'm going to take the value that see how the top right corner, which is the 1AA, in both, or this is the A11 and B, and I'll call this all the little entries of this one because it's matrix B, B11. This is B11 and this is A11. But basically they're saying the number that's in the same exact spot in matrix A as it is in matrix B, add those two together. So that's 2 plus 6, and that'll be 8, and that will be the entry of matrix C, and this is matrix C over here. And this is what they will call C11. That's what they're going to call that term. And then I just do that with every single entry. So that was the first row, first column. Then I'm going to go across second row. I'm sorry, first row, second column. We're going to add those together. And so negative 10 plus positive 10, that's 0. So the entry that's in the second spot in the first row, first row, second column is going to be a 0 for this. Okay? Then we just continue to do this, right? Negative 2 plus negative 2. Well, we have to be careful with our integers, adding integers, but that's negative 4, right? And we have to be, there's a lot, as you notice, there's a lot of calculations that we're going to do here. 14 plus 0 is 14. And then -12 plus negative 12, that is 0. 10 plus negative 4, that's 6. And you guys kind of get the idea, but 4 plus negative 5, that is negative 1. Negative 2 plus positive 2, that's 0. 2 plus negative 2, that's 0. And there is our resulting matrix. So this is the new matrix, the sum of A and B. Okay? So we would write that as our answer over here for this first part, A for 8. So that is the sum. And then now, what is the difference? And it's exactly the same way, but we're going to be subtracting. And what may be easier for you it might be easier for you to multiply every single term in second matrix that we're subtracting. And they say the difference, so they should have actually been more accurate here. They should have said A minus B. I assume that's what they meant, because that would be Sorry for them not being clear with this question. So one way of doing this, the problem that I'm thinking I'm going to have and is that I'm going to have a hard time remembering that I'm subtracting, and I might accidentally add when I meant to subtract, especially since I just got done with adding the terms all together a minute ago. And subtraction is a little bit more difficult because like um, you subtract a negative and it returns positive and stuff like that. So I think what might be better is if instead of doing A minus B, what I can do is I can turn the subtraction into addition problem, but then only if I make the matrix B opposite of everything it currently is. So that might be a better choice to do this. So however you want to do it is up to you, but let's go ahead and subtract it. And I think I'm going to go ahead and do this. I'm going to make everything opposite and then just add it. So it was +6. It's now going to be -6. It was 0. It's going to stay 0. It was -5. It's now +5. It was +10. It's now -10. It's -12. It's now +12. This is now negative, positive, positive, positive. Now let's add them. Because I turned everything negative, I kind of spent, you will think about it this way. Because I applied this negative sign to the B already, it's already spent. So now all we have to do is combine them, which would be addition. One mistake I've seen students do is what they do is they turn everything opposite in the B matrix, and then they also subtract. That would be applying that negative sign twice in two different ways, and that would be actually, that wouldn't be the right way to do it. So now that we're going to add, what we're doing right now is we're adding the opposite of matrix B. And I'm doing that because it's easier for me to add, especially since I added so much in the previous problem. So 2 plus -6, -4. -10 plus -10, -20. -2 plus +2, 0. 14 plus 0, 14. 12 plus 12, 24. 10 plus 4, 14. 4 plus 5, 9. -2 plus -2, -4. 2 plus 2 is +4. And there we go. There is the difference and the answer to this part B. Okay, finding scalar multiples of a matrix, or AKA, you're going to multiply a single matrix by a single number. And actually, I just did that. You just saw an example of me multiplying an entire matrix by -1. So we're just going to do that with a different number. This is the easiest type of multiplication that you could do. So see, they're just saying if there's a number on the outside of a matrix for multiplying a single matrix by a single number, then you're just going to apply that, you're going to multiply each one of the entries by that single number. This is not hard at all. So multiply matrix A by the scalar 3. So I'm just going to multiply every single entry by 3. So that's 3 times 8. It'll be 3 times 1, 3 times 5, and 3 times 4. So the final answer is 24, 3, 15, and 12. And there we go. Not bad. Now what we can do is we can actually now find this sum. So it's saying, hey, take matrix 3 multiply by, take matrix A multiply by 3. And then take matrix B, multiply by 2, and then add the 2 together. We have to kind of follow order operations here, that we would be doing a multiplication here first. So first I find 3 of A. Well, that's going to be 3 times A. So the 3 times 1 is going to be 3. 3 times 0 is 0. 3 times 4 is 12. 3 times negative 2 is negative 6. 3 times negative 1 is negative 3. 3 times 3 is 9. Then 3 times 0 is 0. 3 times 2 is 6. 3 times negative 6 is negative 18. Then we take 2 times B. So this is 2B, and we're going to add these together when you're done, right? Because it says 3A plus 2B. So 2 times negative 1 is negative 2. 2 times 0 is 0. 2 times 0 is 0. 2 times 2 is 4. 2 times negative 3 is negative 6. 2 times 1 is 2. 2 times 1 is 2. 2 times 2 is 4. 2 times negative 4 is negative 8. And then, last but not least, now we're going to add them together. So the first entry, top right corner of this matrix, top left corner of this matrix, top left corner of that matrix. So this first entry will be 3 plus negative 2, which is 1. Then negative 6 plus 4, negative 2. 0 plus 2, 2. 0 plus 0, 0. Negative 3 plus negative 6, negative 9. 6 plus 4, 10. 12 plus 0, 12. 9 plus 2, 11. 8, negative 18 plus negative 8, negative 26. And there we go. There is your sum. Right? Finding the product of two matrices. The product AB is possible if the number of columns of A listed the second number. So if you have a matrix 2 by 3, the columns are the second number listed here. If the columns in A are the same, is the same as the rows in B, then this product is possible. So an easy way to think about that is if you just write the dimensions of A, write the dimensions of B, making sure to do the row first and the column second, then this inner numbers should match. So it's like a domino kind of, that this number there, right? That number there is matching this number here. And if that is the case, then we can go ahead and add them together. I mean, sorry, multiply them and even find a product. A product even makes sense at all. If those numbers are not the same, then it sounds like for right now, we just cannot multiply them. So they show us how to do this. But basically what we're going to be doing is we're going to take our row 1, and we're going to multiply by that row 1 by the column 1. Then we're going to multiply that same row 1 times by column 2. And then we're going to multiply and take that same row 1 by column 3. So we're going to do that. So it's kind of looks like, it's kind of like the distributive property. You distribute that one row to all the columns. Then we're going to do the same thing with the second one. We're going to take the second row, and then distribute that second row to all of the 3 columns of B. And there we go. So it's kind of neat. I remember like the row sort of kind of gets turned like 90 degrees and then gets multiplied by the column. I kind of like that. It's kind of a neat like way to like actually think about it. Okay, so let's see an example. Multiply matrix A and matrix B. Matrix A has 1, 2 rows and 1, 2 columns. So this is a 2 by 2 matrix. The same thing as B. The most important thing is that the number of columns of A is the same as the rows of B. So we have a green light there that we can go ahead and do that multiplication period. So I'm going to take the first row here and I'm going to multiply it by all the columns in B. So 1, 2 is going to be first multiplied by the first column. And then 1, 2 is then going to multiply by the second column. And what's neat about this is when we write the answer, we can write the answer over here. When we multiply the first row and the first column together, that is usually known as the A11. I won't use A because this is the lowercase a seems like it should be the entry from big A matrix here. So maybe we'll just use C. That C is the product. This is the entries of the product, C's. So this is going to be, when I get done multiplying row 1 times column 1, that's going to be entry 1, 1 in the answer. And when I get done multiplying row 1 times column 2, this will be entry 1, 2 in the answer, and so on. So let's go ahead and do these first two multiplications. So it'll be 1 times 2, it'll be 1 times 5. And then what happens is we're going to be adding to get one single entry for a row and a column, because that makes sense, because I need to have one, just like I said, we need one entry in the answer that's row 1, row and column 1. So once I get done multiplying, I'm going to add all of the little numbers together. So it's going to be 1 times 5, which will be 5. Well, I'll write it a little. And I'm thinking in my mind that I'm switching the 1, 2, and I'm turning it 90 degrees, like toward clockwise, so that they kind of line up right next to each other. That's how I'm thinking about it. So it's 1 times 5 is 5 times 1, and then this is 2 times 7. Or 1 times 5, 2 times 7. Then I'm going to add those answers. So it's 5 plus 14 is 19. So first entry, 1, 1 is 19. Okay, so then let's do that same thing with the next one. So 1 times, like I said, I feel like it's better for me to like rotate this and rewrite it like this, like 1, 2, and 6, 8. And then now we're just multiplying across. So 6 times 1, and then 2 times 8. And then 6 times 1 is 6. And then plus 2 times 8 is 16. So 6 plus 16 is 22. So we have 22 as our second entry here. Let me just make sure to add that differently because yep, okay, 22. All right, and then the next one. So now we're going to focus on the second row, right? And we can keep, wait, let me just make sure I have it's in row 1, column 2. So that answer, the 22 that we just got, that needs to go in the first row and the second column, which is right here. So I notice I didn't put the answer here. I put it here, and that's because this, I multiplied to get that answer. I multiplied the first row times the second column, which would be, first row would be this first line going across. Okay, the next thing I'm gonna do is I'm gonna do row 2 by column 1. And I know that that needs to go in the answer. It needs to be the C, it's gonna be the second row, so 2 and first column 1. And the way we're gonna get that is doing the 3, 4 times by the 5, 7. Like I said, I turned this 90 degrees. So what is that? Clockwise. And then that gets me 3, 4, and 5, 7. And now I can just like multiply straight across, like 3 times 5 and 4 times 7. And then I have to add those answers together. So that's 15 plus 28. That's 43. So we have this. This is the second row, first column. So that's right here. Okay, then I'm going to do the second row times by the second column. The second row is 3, 4, and then the second column is 6, 8. I don't actually rewrite this, but I do like to write it in my mind. I rotate this first one 90 degrees and then just multiply straight across. So 3 times 6 is 18. And then 4 times 8 is 32. So then I add vertically 50. And there we go. So there is our product matrix. 19, 22, 43, and 50. There we go. And they want us to note here that when we're doing multiplication with matrices, it is associative. So if there is 3 matrices that we had to multiply together, we could multiply any 2 together that we'd want to. Then it's distributive, meaning that we could have added 2 matrices together, then multiplied by another matrix. But we could have just multiplied by another matrix first and then added those together. We're going to get the same answer either way. Oh, but they do tell us, note that the multiplication is not commutative. And that makes sense. I cannot, if I do A times B, it's not equal to B times A. So we're going to have to make sure that the order in which they are multiplying, that's going to change. And that's going to actually, and because we know that's true because like not all matrices can even be multiplied together, period, if you switch the way, like the ones we saw earlier here, this one, a 2 by 3 matrix, we can multiply it by a 3 by 3, but if you switch those, then you couldn't, right? Because now the rows, the columns in A would not be, right? Because it would be what? It would be 3, 3, by 2, 3, and then the inner parts would not match. So that makes sense why it's not commutative. All right, we have one more like real life example here. They they're given the number of goals, balls, and jerseys that the Wildcats need, and then the goals, balls, and jerseys that the Mudcats, another team, needs. And we are also given the prices on equipment. So one fast way to add and find a total for the equipment is to multiply this matrix times by this matrix. And we'll get the totals for both teams really quickly. So let's just double check this, that we can actually multiply them. We have here 3 rows by 2 columns. And then here we have 3 rows by only 1 column, right? So could I do this matrix? Let's call it A, and that matrix, let's call it B. Can I do A times B? If so, it would be 3 times 2 and 3 times 1. And these inner parts would not line up. So maybe I can do B times A. I hope so, because we can't do this problem. So if I list the dimensions of B first, it's 3 times 1. And A, which is 3 times 2, which the inner does not match either. Oh, I think we can rewrite, because it's like a word problem type of thing, just because this is in a, pretty vertical graph like this does not mean we have to keep this information in a vertical line like that. So we could switch this and make this into a vertical matrix. So, or the same thing, we could choose one and just, I'm going to choose this one, and I'm going to say, I'm going to rewrite this 300 times 10 times 30. And if we do it that way, we should be able to multiply it, because now it's one column, 1 row times 3 columns. And that's fine, because this is, there was no reason why they had to write it vertically here. So we're going to choose to write this as a single row matrix. And now it'll be 1 row times 3. And now we can do, now the inner ones will match. So we will end up multiplying these times by those two. And it makes sense. I have to multiply everything here times everything in the first row. And it's just a fast way to just find up all these totals. So I'm going to take this row and multiply it by the first column of the Wildcats. So this will be in the product. This will be C, and it's the first row times the first column. So it'll be so we'll multiply 6. And like I like to do it, I like to just move this, turn it um, like this. Now we can see more clearly exactly which numbers need to be multiplied. So it's 300 times 60. I'm sorry, 300 times 6, 1800. Then 10 times 20, 200. 30 times 14. Well, 3 times 14 would be 42. And that was a 0, so 4,200. And then we would add those all together. So it'd be 0, 2, 6 plus 8, 14, and 2,420. So that's going to be our first, erase this right here, our first row and first column in the answer. This is our answer, C. So it's 2,420. Then we're going to take that our first row, which is the only row, and multiply it by the second column. So this will be first row, second column. It's going to be 300 times 10 times 30 times by 10, 24, and 20. 10, 24, and 20. Okay, and then I'm going to rewrite that 300, 10, 30. Then 300 times 10 is 3,000. 10 times 24 is 240, and 20 times 30 is 600. We add them, 0, 4, 8, and 3. So it looks like 3,840. And there we go. That's an example of a real life type of example. Of course, we could do this. I mean, if I asked you to figure out how much money the Wildcats actually spent on their equipment, you would just take 300 and multiply it times 6, 10 multiply it times 30, and 30 and multiply it times 14, which is what we did, and add it all together, which is exactly what we did. But you can imagine, and I know maybe this process, you're just like, I don't understand, but like if there was like, you're working for a large business and there's lots of different expenses and you wanted to quickly find totals, you can make it, what we will eventually learn is a calculator can do such calculations. And if we understand these smaller problems, we can understand correctly how to input later on information to our calculators. All right. I hope you found this helpful. And let me just, one more thing. Oh, okay. Oops. I noticed that I made a small error there, an arithmetic error. And I'm kind of glad I made this error because it is so easy to make. There's so many little, as you can see, there's so many little calculations that go into one single problem. So I think I went a little too quick and I did 14 times 3. And one of these calculations I did incorrectly in the first answer here. So I think it should be 2520, I believe, and this would be 3840. So let's just double check all our answers here. It's 300 times 6 and making sure that we wrote the correct matrix, 6, 30, and 14. And then yeah, that's 1800. And then 30 times 14 equals 420. So 420 plus 200 plus 1800. Well, I still get the 2420. So I don't see, I may have made a arithmetic error here, but at the moment I don't see it. And everything else looks good. All right. Let me know if you can find the arithmetic error. But it looks like there's no problems the way we multiply it. Have a great day. Okay, bye-bye. No procedural problems. Bye.